Okay, hello everybody. Today I'll be talking about energetic of ionic bond formations. So first, let's get into some physics. I know you guys might not have taken physics before or whatever, but I'll teach you. First, let's understand what work done by a gas is. First of all, let's say let's say we have some let's say we have some gaseous particles in this box, like some gases, right? So naturally, what do these gases naturally want to do? These gases naturally want to expand, right? The gas wants to expand. So when the gas is expanding, right, who's doing the work? The gas is doing the work. So this is what we call work done by the gas. But let's say if the gas is slowly compressing, you have to put force on it so it could compress. So what's going on? Work is being done by the gas. So this is what the work is being done on the gas when the gas is being compressed, right? So when the gas expands and goes up like this, right? That means work is being done by the gas. That means the volume is increasing. So when the volume is decreasing, like this, like that, right? That means work is being done on the gas. So that's just to give you a gist of what that means. Okay. So let's say we have this PV diagram, and let's say this is the process. When this, let's say this is the process. When, and let's label this point A and point B. So when this process is going from point A to point B, what's going on? The volume is increasing, right? And that means work is being done by the gas. So let's lay, and then we know the work done from A to B would be like the total area under the curve. So it'll be this, the whole area under the curve, right? And then let's say we're going from B to A. The work is being done on the gas. So and the total work for that would be this. Everything under this area for the work being done on the gas. So you have this area that's left, and this area is called the net work done on the system. This is what we naturally call the net work, right? Done by the system. The net work done by the system. Why is it done by the system? Because, well, it's this area compromises the area that when the gas is expanding. So it's the net work done by the system. So the change in internal energy, which we would define as change in internal energy, which we would define if it's a monatomic. Let's assume it's a monatomic gas, and then the net work done by the system is the total kinetic energy. Is the change in kinetic energy on the system. So let's define that as. So let's define the change in internal energy. Let's define the change in internal energy as uh, the heat transferred or taken away from the system, subtracted by the work done by the system. This is what we will define as the change in internal energy. Okay, so we got that. So basically, change in internal energy, like gravitational potential energy, is something called a state variable. And a state variable is dependent only on your initial and final states. It's independent of the path taken. So let me write that down, right? So this is what a state variable is. It's dependent only on your initial and final states. And it's independent of the path taken. So imagine we have, like, for example, enthalpy, which we will be defining here. Enthalpy, which is represented by H, is a state variable. And its formula is so the change in enthalpy would equal this. would equal the change in internal energy plus the change in PV. So we know from before, right, that the change in internal energy equals Q minus the work done by the system. So, oh, something I forgot to mention. If the work was being done on the system, you would put that negative work, being done on the system here. So you would get Q plus W. Okay, because we define as work being done on the system as negative. So you put that negative, you would replace the negative work here, and then the two negatives would become a positive. So the change in internal energy for the change in enthalpy would equal to Q minus the work being done by the system, right? The work being done by the system plus change in PV, right? So work could also be defined as P change in V. Now work could only be defined as P change in V when when you have constant pressure. Right? Because when you have constant pressure, the area under the curve would just equal the change in volume multiplied by the pressure. This would be the work. Well, in most reactions, the pressure is the same. So it is legit to write P change in V in this case. Right? P change in V plus change in PV plus change in PV equals the change in enthalpy. Right? Change in enthalpy. So right away, what can we cancel? We could cancel these two variables because we already know it's equal. Why is it equal? Well, for this following reason. It's equal because the change in the pressure, because there's no change in pressure, the pressure stays the same. So these two must be equal. So that means and if this is a negative and this is a positive, these two must cancel. So let me just write the mathematical formula for why these two must be equal. Well, for example, we know minus P change in V could be written as, so what we have to prove this basically. P change in V equals change in PV. We have to prove this in order to cancel these two variables. So P change in V could be written as P, right, times V final minus V initial, right? And change in PV could be written as PV final minus PV initial minus PV initial minus PV initial. So if you factor everything, you would get P change in V, P VF minus PVI, yeah, equals P final times P final V final minus P initial V initial, right? So if all the P's, if the P, which is the pressure, is kept constant, if P is kept constant, that means P final equals P initial. That means P final equals P initial. So basically, if that's true, then we could write, If that's true, then we know for sure that, then if that's true, then we could cancel all the finals and initials, the subscripts in P. So we could cancel this and this, since the pressure stays the same, right? Since this pressure would equal this pressure would equal this pressure would equal this pressure. So we could just cancel all the variables all together. This cancels with this, and this cancels with this, right? So we get that. So that means these two variables must cancel. So you have the change in enthalpy equals to the heat transferred to the system. Heat transferred to, or transferred to the system, or taken away from the system, basically. So it could be positive or negative. And this is in chemistry. In physics, we would call this change in enthalpy. Yeah, change in enthalpy. But in chemistry, you naturally call this heat of fusion.